and dear fellow students, on behalf of convener and organizers of 5th Professor D.B.Ingle Memorial Lecture Series, I welcome all the participants who join online and offline. I request all the faculty members to offer garland and flowers to the photographs of Chhatrapati Shivaji Maharaj and Bharat Ratna Dr. Baba Saheb Ambedkar. I request all the faculty members, please come on the dais. I request all the senior faculty members. नाही दिसतंय त्यांचं दिसतंय, दुसरं कॅमेरा लावलेला आहे त्यांनी, तू इकडंच करते. हां May I now request all of you to pay humble tribute to late Professor D.B.Ingle for his 5th death anniversary. I request all of you to please pay tribute. Kindly stand up. Thank you. Thank you, all of you. Today, we honor the legacy of late Professor D.B.Ingle and remember the invaluable contributions of all our esteemed professors. Their dedication and guidance have shaped countless careers and elevated our department to new heights. I request Senior Professor Suresh Gaikwad sir from Department of Chemistry, Dr. Baba Saheb Ambedkar, Marathwada University, to brief about late Professor D.B.Ingle to the budding chemistry students and fellow participants.
Very good morning to one and all. Good morning. So I am here to present before you the brief introduction of late Professor D.B.Ingle sir. So as you are well aware about, we are assembled here for a 5th lecture series of late Professor D.B.Ingle sir. So first time we are going to conduct in the department. Earlier also it was conducted, but in sometimes MGM, sometimes Vivekanand College, and sometimes some other colleges. So this time we took this opportunity to have this lecture series of our late Professor D.B.Ingle sir. And for this program, many of students from MSc first year and second year, they may not be knowing our senior faculty who work here for long time, like Professor Y.S. Deshpande sir is with us, Professor M.S. Shingare sir is with us, Professor S.W. Rajbose sir is with us, Professor Dr. Arbad sir is with us, and even the professor, retired professor from biochemistry, Dr. Baburauji Somowanshi sir is also deliberately here, and that is for attending this particular lecture series. So first of all, I welcome all these dignitaries, those have served for a long time for particularly the Department of Chemistry and this university. I welcome them, and I also welcome all the participants, those who have participated for this lecture series, maybe research scholars, MSc first, second year students, and I also welcome today's speakers and chairman of this lecture series, Pol Chettiwar, Dr. Bhaskar Sathe sir, and chairman for that lecture series, we have C.V. Raman Awardee and one of the best alumni of our department, Dr. Satish Patil, who is serving as a senior scientist at Indian Institute of Science, Bangalore at present. So you must be knowing about late Professor D.B.Ingle sir, and I am specifically, it's my pleasure because D.B.Ingle sir is from my taluka place. Our native place is very nearer to one another. Just 5 kilometer distance was there. My village is Kolpimpri and sir's village is Kalamamba, and both are in the same taluka earlier. Then Kes taluka, now it includes in Dharur taluka. And as you might be knowing, he is from farmer family, and even though he touched this particular level, so late Professor D.B.Ingle sir served as a professor and head Department of Chemistry, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. Now it becomes Chhatrapati Sambhajinagar, and that is for a long time, more than 35 years. He came from farmer's family and was the first learner from the family. Actually, not from the family, but I may say from whole taluka. There was no earlier learner for this type of education. He educated at Ambajogai and then he shifted to Aurangabad. Another one coincidence is there, from which school and college education he learned. From the same school and college, I also completed up to graduation from Yogeshwari Education Society, Ambajogai. He earned SSC standing second in the order of merit from the then Usmania Education Board, Hyderabad. He obtained BSc and MSc in organic chemistry and MSc in physical chemistry also. He was double MSc. From the Marathwada University, the then Marathwada University, by standing first in the order of merit. And he received PhD degree in chemistry under the able guidance of the then late Professor D.D. Khanolkar sir, who also worked as a founder, head of the chemistry department of this university. He was closely associated with Millen College of Science as he graduated student and always received blessings and guidance as a foster son of the then principal Dr. M.B. Chitnis sir. I must say a few words about M.B. Chitnis sir, in whose association Ingle sir also got for a long time, because M.B. Chitnis, who was the founder principal of Millen Science College, that time there was no university. All PG courses were conducted in the Millen College. And M.B. Chitnis, who worked under the guidance and in association with Bharat Ratna, Dr. Babasaheb Ambedkar, that time. And I saw many photographs of Dr. M.B. Chitnis sir with Dr. Babasaheb Ambedkar, as there was one memorable photograph, and that is at the time of establishment of Millen Science College, Aurangabad, and that is with architect of Millen College, Aurangabad, along with Dr. Babasaheb Ambedkar, Principal M.B. Chitnis, Srimati Savita Ambedkar, Rao Bahadur, and B.H. Varale. So that is a very memorable photograph of Dr. M.B. Chitnis, sir. Another one thing I want to put, because in whose association Dr. Ingle sir learned many things, and he was able to complete his education of MSc. Principal M.B. Chitnis was a contributor to the book Babasaheb Ambedkar and the Movement of Untouchables, volume number 1. And the book that time was published by the Maharashtra Education and Social Welfare Department of Government of Maharashtra. So, in the association of M.B. Chitnis sir, so many of the things get inculcated in the personality of Professor D.B.Ingle sir. He extended his services with Department of Chemistry as a teacher and researcher and earned recognition as a well-known physico-organic chemist. He taught fundamentals of organic chemistry, organic reactions, mechanism, stereochemistry, and spectroscopy to the synthetic organic chemistry includes biodynamic heterocycles, chemical kinetics and coordination chemistry. He guided more than 25 students for their PhD and published more than 100 research articles in the journals of international repute. That time 100 number is very great number. He extended his services as a member of Senate, Academic Council and Board of Examination of the then Marathwada University Aurangabad, and provided relevant academic services to the universities within the state and outside the state by keeping focus on quality in higher education and inclusiveness. In view of his academic and research contribution, the government of Maharashtra honored him as an ideal teacher in the year, I think, 1996. He had not only served as a teacher and researcher, but always played as a guardian and parent of the student associated with him. Because of his inspiration, motivation, and proper guidance, a large number of students have pursued their career in chemistry as a researcher and teacher and in private sector also. Most of his students are found to be extending their services in national institute and corporate sectors by shouldering valuable responsibilities, particularly National Chemical Laboratory Pune, Indian Institute of Chemical Technology Mumbai, Indian Institute of Technologies at various places in the country, even in IITs also, central universities and state universities. Many students are working with corporate sector, particularly in R&D for pharma and polymer industries. He always recognized the rural student of this region for selecting chemistry and allied subject for their future career. In view of his contribution for shaping career of many number of students and their associates, and almost all his students have decided to arrange distinguished lecture series in respect to his memory on his death anniversary. Death anniversary is actually on 30th of November, before 5 years. But due to one or the other reason, the organizing committee could not conduct, maybe due to the dates of resource person or guest. So it is extended, and for the purpose we are assembled here to have a lecture series. Instead of 30th of November, we are conducting today, that is on 7th of December. So once again, I welcome, and definitely all the research students and MSc students will be beneficial by this particular lecture series of late Professor D.B.Ingle sir. So I have no doubt about that, and I request you all carefully listen all the lectures, and lectures of first lecture will be of Bhatnagar awardee Pulshettiwar, and another lecture is from our faculty, Dr. Bhaskar Sate sir. Thank you very much.
Thank you, sir. We now move towards one of the highlights of our lecture series. May I now request Professor and Head, Department of Chemistry, and convener of the program, Dr. S.G. Shankarwar sir, to say a few words about organization of the lecture series and introduce the chairperson of the first session.
Good morning, one and all. On behalf of the Department of Chemistry and organizer of 5th Professor Dr. D.B.Ingle Memorial Lecture Series, I welcome you, all the participants and distinguished speakers. I feel proud and honored to host this 5th Memorial Lecture Series in the Department of Chemistry, which remains workplace of Professor D.B.Ingle. Already you have heard about the contribution of Professor D.B.Ingle in advancing the chemistry from Professor Suresh Gaikwad. I will be highlighting the objective of the lecture series. Every year on the date anniversary of Professor D.B.Ingle, the organizer used to arrange the lecture of distinguished academician and scientists for enlightening and motivating the budding and active chemists to update them in the recent trend of chemistry. First time, the Department of Chemistry is organizing this 5th Memorial Lecture Series to motivate the young researcher of the department and region. This has been arranged in hybrid mode. The distinguished speaker invited for this purpose are Professor Vivek Polsettiwar, TIFR, Mumbai, and Professor Bhaskar Sathe, Department of Chemistry, Dr. Baba Saheb Ambedkar, Marathwada University, Chhatrapati Sambhajinagar. Now, the chairman of the first session is one of the alumni of this department, Professor Satish Patil, IISc Bangalore. I am happy to introduce him in the brief. Presently, Satish Patil is shouldering the responsibility as head, Department of Solid Structural Chemistry Unit, IISc Bangalore. After earning Master of Science degree in Organic Chemistry with distinction in 1998, he joined for PhD degree at University of Wuppertal, Germany, and obtained the degree in 2004. He worked as a postdoctoral research associate at University of California, USA, during 2004 to 2006. He started his academic and teaching career joining at IISc Bangalore as assistant professor from 2006. He then elevated as a professor in the same institute. He has recipient of various awards, prize, and fellowship. He is also on editorial board of various well-recognized journals. He has significantly contributed in the field of polymeric materials. In this year, he has been bestowed by prestigious C.V. Raman Award for his research contribution. On behalf of all of us, I heartily congratulate Satish Patil for the achievement and request all of you to give him stand ovation. And now, request Satish Patil to take the charge of first session and commence the session. Thank you.
Okay, I think I hope I am audible. Yes. I have no words to express my gratitude to all my teachers. If you might sound is echoing, perhaps maybe you can mute that. Hello? You can mute that, yeah, you can mute on that computer. Better now? Yeah, okay, all right. I hope I'm audible to all the people there in the auditorium. Okay, all right. So I think, yes, so, I'm deeply, sort of humbled by this sort of remarkable teaching experience I had in Aurangabad. My journey is something is very fulfilled. I would say my stay in Aurangabad during for 2 years, my masters was very academically fruitful. I had wonderful teachers to teach. I name few: Professor Goswami, Professor Jagirdar, Professor Arbad, Professor Mani, Professor Palaskar. I think when I entered, or soon after my BSc, I had an incredible number of teachers to teach the basics of fundamentals of chemistry. And that motivated me to pursue science as in a career. I also remember fondly Professor Deshpande's wonderful stories. In between our inorganic chemistry lectures, he used to tell us very inspiring stories of many scientists, and that has really motivated me, sort of again to take a path of scientific journey. So I think with my brief words, I'm thankful to every member of Dr. Baba Saheb Ambedkar University Chemistry Department, all my teachers, students, and all the academic fraternity of the people who are associated with that remarkable place. I'm very thankful for all of you for your contribution in my journey. So, with this brief introduction about me, I'm very delighted to introduce my close friend, Vivek Polishettiwar. Me and Vivek, we know each other. We don't meet very regularly, but yes, we have a huge respect for our academic journey, what we are doing independently in TIFR in IISc. And I must say that Vivek also had a humble beginning, and his academic story is also very inspiring for many of us. He also coming from a small place, but that did not limit him to dream very big. And today, what kind of science is practicing at TIFR is the best science one could do in this country with this ecosystem. So he's competing best in the world. And with this brief word, I must say Vivek has now currently the professor of chemistry at Tata Institute of Fundamental Research in Mumbai. His research.
गवर्नमेंट सेक्टर में लगा था उसका.
Sorry, can you please mute others? Yeah. Others can mute. There is some, I think organizer can mute. Dr. Megha Rai, can you please mute? Okay, all right. So he started working on a nanomaterials. I think his main area of research is how to develop a advanced nanomaterials and in particularly harvesting solar energy and how you convert a carbon dioxide. That's a major problem, for into today's world, into valuable chemicals and fuels. He's sort of, recently his work has been recognized with many awards. I will read few here. His was awarded International Union and Pure and Applied Chemistry Prize for Green Chemistry in 2022. He also received the following was award in Physical Sciences. The following year in 2024, he was elected as a Fellow of Indian Academy of Sciences here in Bangalore. And in 2024, he received the Shanti Swarup Bhatnagar Award from President of India. That's one of the highest awards in the country for a younger scientist. With this brief introduction, I request Vivek to begin his talk, and thank you very much.
Thank you very much, Satish, for your kind introduction, and I'd like to thank everyone, for all the organizers, for giving me this great opportunity. I think it's my honor to present Professor Ingle Memorial Lecture. So let me share my slides. Satish, can you see my slides?
Yes, sir. Yes, sir.
Yes, it's coming. Yes, yeah, we can.
So once again, it's truly my huge honor to give this Professor D.B.Ingle Memorial Lecture, and I'd like to thank the organizer for this opportunity. I think we share the similar journey. I also come from a very small village and trying to do a science which will impact not only the scientific society but the real society. And we all know we are struggling with lots of issues. And one of the key issues is the climate change. I guess we all know climate change is one of the most serious problems that mankind is ever faced, and we need to find a way to tackle the climate change.
Hello.
And that's what my group is trying to do. We are trying to develop a range of nanomaterials which can harvest solar energy, which can act as a catalyst, and they can convert CO2 into useful chemicals and products, and that possibly allow you to achieve some sort of a cyclic economy, cyclic carbon economy. And this is what I'm going to present today. So I guess we are all experiencing this global warming, or climate change. It's not only heating, but sometimes heavy rain, or sometimes farms are becoming desert. So we all know it's because of the climate change, and we all know this is because of carbon dioxide, one gas molecule. Obviously, there are some other greenhouse gases, but CO2 is the key. If we tackle the CO2, we ideally can combat climate change. And in terms of our country, our CO2 emission is going to increase with every day passing. We're going to emit more and more CO2 because we want to be a developed country. So that means you need more fossil fuels, more cement, more steels. We need everything almost. It's increasing in a non-linear fashion. So currently we are emitting around 2.7 billion subtons, which is a huge, huge number. And the slope of this graph is going to be even steeper, and we're going to have a huge amount of CO2 emitting in coming years. And this cannot be stopped, right? So that means we have to use the fossil fuels, we have to use coal, right? Because see, even today, less than 15% of the energy comes from the natural resource, renewable resources. Mostly it's still carbon-based fuels. So if that is the case, then if you still want to use the fossil fuel as one of your energy source until we replace them by the renewable sources like solar or hydrogen or electricity. What can be done? What can be done so that we can continue using the fossil fuel? And one of the best ways to convert the emitted CO2 into some useful chemicals. So it's not the capture which is going to solve the problem, because if you even capture the CO2, what will you do with the captured CO2? You can store somewhere below the seabed or something, but it can always leak and it can always come out. There's huge risk. So the best solution is to convert CO2 into useful chemicals, and one of the reactions that our group thinks would be the best way is you react CO2 with water using sunlight and get you carbon monoxide and hydrogen. And mixture of carbon monoxide and hydrogen is known as a syngas. And it can, once you convert CO2 into a syngas, mixture of CO and hydrogen, you can convert syngas into a range of chemicals. And in fact,
Professor Vivek, can you make full screen?
oh, it is full screen. Not at your end?
No, I think it's full screen, Vivek. It's fine. It's fine.
Yeah, it's full screen, yeah.
Yeah. It's good. Yeah, please go ahead.
Yeah. So the idea is to convert CO2. So react CO2 with water.
Hello.
Water is free. Then we also have a sunlight, which is ideally free. So you are using excessive waste CO2, reacting it with water and using sun's energy. You can convert them into CO and hydrogen. And if you are successful in doing that, CO and hydrogen is known as syngas, and you can convert the syngas. You can use the syngas to make almost all the chemicals that we need every day in industry and everywhere. So you can see now the bottleneck is very simple. It's just taking out one oxygen from CO2 and make it CO and get hydrogen, right? So if this is so simple, if this simple reaction can really solve the problem, then why is this not happening? Why this process is not still commercialized at an industry scale? Obviously, there are lots of work at lab scale. And if we achieve this, you can see this term, I guess most of you know, circular carbon economy. That means I develop a catalytic system which works with light, which works in presence of light, and then you react CO2 with, say, a green hydrogen or water directly and convert CO2 to different fuels. Say, for example, methane, which is your CNG. Burn methane, get the energy, and use that energy to do the work, say to drive a car or something, or an engine. And the CO2 that is emitted while burning the fuel, that CO2 will go back to your catalytic reactor, your catalyst, and again convert it back to the fuel. So if this is an efficient process, you can see in this entire cycle, no CO2 is emitted. Now ideally I started using CO2 as my carbon source, as my fuel source, rather than CO2 as a waste. So if this is so good, why it is not happening? And I guess we all know CO2 is extremely stable molecule. It's sp hybridized linear molecule, so it's a thermodynamically extremely stable. So why will such a stable molecule will convert into any other molecule? For that, you have to overcome huge activation energy barrier, and that makes process sustainable. You cannot put in that much of energy to convert CO2 to something else. So now the idea is then, what can be done so that I reduce the activation energy barrier, or find a process, different path with a reduce activation energy barrier. And that's what we are trying to do. We're trying to develop nanomaterials, which has these very high surface area, and not only the surface area, but it has a high surface energy, very reactive surfaces. So when CO2 go and sit onto these surfaces, you bend the CO2 molecule. The two oxygen get pulled towards your surface, and that linear CO2 becomes bent CO2. Sorry. And that bending is enough to reduce the activation energy barrier. Obviously, you can stretch, more you bend, more you stretch, you will again reduce the activation energy barrier. However, even after activation, we need to find a material which can activate CO2 and bend it. Even after that, you will still need some amount of activation energy barrier. You still need to overcome some amount of activation energy barrier, and that can come from the solar energy. So that entire process becomes sustainable. So what it means is, now you need a material which first capture and activate the CO2, it can be solved onto the surface of the nanoparticle, and at the same time, the same material should also have the ability to harvest the solar photons. They take the photons from the sunlight, then you can either follow the mechanism of photon to electron, and the electron do the reaction, or photon to thermal energy, and you can use that thermal energy to localize onto the surface of the nanoparticle to carry out this reaction. So our group's aim is to design a material which does both the function: activate the CO2, act as a catalyst, as well as it's also a photoactive material and harvest the solar energy. So how do we design these materials in our lab? So we work on a heterogeneous catalytic system. That means we use these high surface area materials, and onto which we put some active sites. So high surface area materials will help you to capture the CO2, to capture the photons, and these active sites really does a catalytic reaction of CO2 with water or CO2 with hydrogen. So the first condition to design a good heterogeneous catalyst is you need a high surface area material. And this is the material that we discover in our lab. We call it as a dendritic fibrous nanosilica. It's ideally a silica with a nanoscale size. Size can be 50 to 100, 100 to 200. You can go up to 1200 nanometer. That allows you to tune the surface area from 500 to 1200 meters per gram. It has excellent thermal stability, so you can heat up to 800 degrees Celsius. That means you can carry out the processes which are high temperature. It has excellent mechanical stability, that means you can do high pressure reactions, and it's easy to synthesize. We don't use any complicated processes, it's just a solvothermal mixing of some precursor solvent and heating. For a few hours you get this product. And the uniqueness is it has a fibrous surface morphology. You can see these are not plain spheres, they are not a smooth sphere, they have these fibrous structure like a prajandus of food, right? A marigold flower in a 3D. So then in our lab, in addition to developing a new material, we also try to ask this question, a fundamental question, that why my material has such a fibrous structure, why it is spherical, why not a flat structure or some other shape. So in order to understand the mechanism, okay, so you can see here these are highly monodispersed particles. Now in order to understand the mechanism of the reaction, we need to understand how we synthesize it. So silica synthesis is ideally very easy. You take in silica precursor, see this is a tetraethoxysilane. You hydrolyze, you get a silicic acid, you again then condense and polycondense, you polymerize the silicic acid, and you get a SiO network, which is your amorphous network of siloxane, which is your silica, the one you use in your lab. But when you do this, you get a bulk silica. There is no control over the size or the shape. Now, in order to bring in the control over the size of the nanoparticle as well as the shape and the morphology of the nanoparticle, what we do is we use these templates. We use these organic molecules which can form a template at a nanoscale, and then you do your synthesis of silica within those templates. So how do we synthesize the template or prepare a template? You use the CTAB molecule. So CTAB has this polar group, quaternary nitrogen, which is shown as a blue ball in your cartoon, and then it has a CH2 up to 16 times the hexadecyl group, which is a non-polar, right? And this non-polar is shown as a this zigzag line, right? So I will show you so what will happen if we add these surfactant into some solvent. We know they generally form a micelles, reverse or normal micelles based on what solvent we use. So I will show you the animation to explain this in a better way. So these are the CTAB molecule. You can see a blue ball as a polar nitrogen head, and the zigzag line, the gray zigzag line is the CS2 CH2 times. We added these into a mixture of a water and xylene, so it's a xylene water mixture, and concentration of CTAB is such that they form these lamellar phases rather than normal micelles. Now you can see in these lamellar phases, there could be repulsion between these quaternary nitrogens, so we add one more co-surfactant, say pentanol or hexanol, having these OH as a head and the tail, and they will go in between this and they reduces the repulsion and stabilizes the interface. What we observe is these are not floating flat into the solid. If it is a flat, you get a flat surface 2D material, but they are in the form of a droplet. We call them a bicontinuous microemulsion droplet. These are actually a spherical droplet, bicontinuous because we are using cyclene and water and they are trying to mix continuously. So these are the template molecules made up of a xylene, water and CTAB and some amount of urea as a hydrolyzing agent. And now silica precursor is in there. As soon as you heat, silica hydrolyze and you get a silica exactly like these droplets. Now we also learn to merge them together. If you want a bigger particle, then you merge many of these droplets together to get you a bigger droplet. And if you get a bigger droplet, your nanoparticle will be big. If you keep them away from each other, you get a very small droplet and your nanoparticle will be of a smaller size. So that's how we were able to tune the particle size from as small as 50 nanometer to as big as around 1.2 micron size, around 200 nanometer. Okay, so this was all about the synthesis and mechanism of the DFNS. But the problem is, this is the silica, SiO2, this is an insulating material. And what I started my presentation is, we need a material which is not only high surface area and proper morphology, but they have to be photoactive. They need to harvest the photon. And obviously the second thing is they also need to have the active site. So silica has none of that. Silica neither absorbs the visible photon, it is a large band gap, and it is also don't have any active site. So now, how to design a catalyst which harvests all the solar photon coming from the sun as well as also acts as a nanocatalyst. So to design a photocatalyst here, we use the concept of plasmonics. So what is the plasmonics? In a simple language, we all know the gold jewelry, the gold that we use is shiny yellow color because the gold, all the metallic surfaces has this electron cloud onto the surface. So that electron cloud reflects all the photon coming from the sunlight except the blue portion of it, and that's why gold is yellow it's the golden yellow color. However, when you convert that gold into a nanoparticle of certain size, say 10 nanometer, then the electron cloud onto the gold surface, onto the gold nanoparticle surface, that cloud is polarizable now. So when light comes in, it now, rather than reflecting the light photons, it will now start interacting with those light photons, start interacting with the electric field of the incoming light, and at one particular wavelength, the natural oscillation of the electron cloud on the nanoparticle matches with the wavelength of the light, and there is a resonance. And that resonance is called surface plasmon resonance because it is happening on the surface of the nanoparticle. And since it is localized onto the nanoparticle, it is called localized surface plasmon resonance, LSPR, and that's what we are trying to use in our system. However, we should also ask this question, okay, you can harvest the light using the LSPR. What will happen when the LSPR is dephasing, when it is broken? So when LSPR is dephases, that entire light energy that is now harvested by these nanoparticle is get damped onto the surface of the nanoparticle. This is very important. It damps onto the surface of the nanoparticle, and catalysis is also a surface phenomenon, and I will try to explain this in just like how this helps. So when the energy damps onto the surface, what will happen? You will have that electrons at the ground state taking that energy and go to the excited state. So you can have S2S transition and D2S transition, and you can imagine the D2S transition is obviously prepared transition. So now, because of these damping, you now have an electron in an excited state above Fermi level, and in this field it is called hot electrons, more like excited electrons, but they are different a little bit. So these hot electrons, now you can use these hot electrons and inject into the CO2 molecule. So what will happen? CO2 becomes CO2 radical anion, and which is very reactive. So you automatically reduce the activation everywhere. However, the challenge is the lifetime of these electrons, hot electrons, are less than tens of femtosecond. So the possibility of using them is very little, although there are some reports of using the whole venture to use it. But when they relaxes back, they undergo electron-electron collision, right? They collide with the electron which is in the lump state, and they create some sort of a secondary hot electron, secondary family of the hot electrons. It's also known as the Fermi distribution of energetic charge carriers, which is somewhere above Fermi level with a lower energy than the normal hot electrons. But they now have a higher lifetime, longer lifetime, and there is a possibility of using them for a CO2 reduction, and that's what we are trying to do. However, if you miss these hot electrons also, then they undergo electron phonon coupling. So they collide with the vibrating atoms, and all that energy that was harvested because of the LSPR, those photon energy is now converted into heat, and more importantly, that heat is localized onto the surface of the nanoparticle. And now my catalysis is again happening onto the surface. So I can efficiently use that heat for a catalysis, right? You don't need to heat entire bulk thing now. You are only heating the surface, and you can still carry out the reaction. So there are two ways of carrying out the reaction. One is use photon, generate hot electron, and carry out the reaction, or use photon, generate these thermal hotspot or a thermal energy, thermal heating of the surface, and carry out the reaction. So photoelectron or a photothermal, there are two ways of doing the catalysis, and I will try to explain which is the way that we observe in our processes. Okay, now another challenge in the field is, if I just take a 10 nanometer gold particle and put it on our silica, it absorbs somewhere around 550 nanometer and a very weak absorption in other part of the wavelength. However, to design a good photocatalytic system, you want to harvest every single photon coming from the sunlight. You want something like this, a broadband light absorption, maybe starting from UV to near IR. Now we ask this question that how do I get a material, how do I synthesize a material which can have a broadband light absorption? Literature says if you change the size, there could be possibility, but you see now, if I change the size from 9 nanometer to 22 to 48 or 99, you're only changing the lambda max, you're not broadening it. You're maybe a little broadening, but nearly it's just a lambda max change, it's not harvesting all the photon. But then there was, in the literature, there was this concept which says that if you bring the gold particle closer and closer, the plasmon of one gold nanoparticle interact with the plasmon of another gold particle. And this is called a plasmonic coupling, and that allows you to broaden. So we try to then develop on this concept and see, can we now find out, rather than taking only two particles, can we take multiple particles, bring them together so that there will be multiple plasmonic coupling, and ideally you get a broadband light absorption. That was the hypothesis, to bring multiple gold particles close as possible. Now the question again is, how do I do that? How do I tune the distances between the gold particles? You cannot do it in a solvent phase, right? Because they will be randomly moving around and there is no control, right? You can put in some linkers, but then we all know that once you put the light, it generates the hot electrons. So these hot electrons will break down those linkers, and then the particle will come closer. We wanted them at certain distances so that there is a coupling. If they connect, there is no coupling. So then we came up with this idea of making these nanoparticles using the concept of nucleation and growth. Quickly, nucleation happens when you have a concentration of your reactant above supersaturation. If you are below supersaturation, then there is no nucleation and only growth happens. Now what we did, we took those silica sphere, I am showing only one silica sheet of that sphere, functionalized with amine at an equal distance, and then created these small gold seed using the nucleation state. So that's the cycle 1 or cycle 0. And then in the second cycle, what we did, we stayed below supersaturation so that no nuclei will form and only the existing gold particle will grow. And using that, you can see when you grow the existing gold particle in every cycle, the distance d is decreasing. And that's what we wanted. We wanted to decrease the gaps between the particle, and at this stage we don't know what is the optimum distance. So we prepared range of a material to find out what is the optimum distance between the gold particle required, so that you get a proper plasmonic coupling and a better light harvesting. So we carried out 0th cycle, 1 cycle, 3 cycle, 4, up to 6 cycles. Now you see the data. Now you can see in the form of a color, C0 is this. It's a very weak absorption. You don't see it here. You have to zoom in. But as soon as the particles are going closer, so C1, C3, C4, C6, you see the light harvesting ability becomes broader. Now it is harvesting almost C4 and C6 is harvesting most of the photon coming from 400 to 1100 nanometers. So you are harvesting all the photons coming from the sun, and because of that, the color becomes black. So black color is not important because it is black in color, because you also have carbon and lots of other materials is black in color, but this black meaning every photon that is coming from the sunlight is being harvested, complete broadband light harvested. So, and this is because of the plasmonic coupling as well as some input from the heterogeneity of the particle size. Now we were very excited. We said, okay, wow, we got a good photoactive material which can harvest entire spectrum of the sunlight, so it should show good photocatalytic activity. So that was our hypothesis. We carried out this reaction, CO2 plus water in the presence of black gold. DPCCX is a black gold, and using the visible near IR light, and CO2 plus water gave us a methane, not CO in this case, based on silicon. Now you can see the black gold activity is 10 times better than the normal 10 nanometer gold particles supported on silicon. So you got a better 10 times better activity than the conventional 10 nanometer gold. So indicating that there is a role of a plasmonic coupling. However, if you look at the data again, just 1.5 micromole per gram, that too in 6 hours, right? That's a very, very small number. So then we ask this question that why methane yield is very low when we are saying that we develop this black gold which can harvest all photons coming from the sunlight, then activity should have been very high, but somehow it is not. Activity is ideally very poor. So we ask this question why it is poor. Our hypothesis was, although black gold is able to harvest lots of photon and possibly able to generate lots of hot electrons, they are recombining back with the hole because of the short lifetime, and we are not able to inject those hot electrons into CO2. So in order to answer that question, what we did then, we said, okay, let us take one more active site, say nickel, because nickel is known for CO2 absorption nicely. So let us take a black gold and a nickel sitting onto the black gold, and what will happen now? Nickel has empty states, nickel has lots of these empty states. So as soon as you develop, so the blue color is black gold and this is a nickel. So as soon as you develop the hot electrons in the black gold, and because nickel is sitting onto the surface of the black gold, the electrons will inject into the unoccupied metal state of the nickel. So now electron will be in the nickel state, holes will be in the gold. It creates some sort of heterojunction in a semiconductor, although we don't call it as they say in the plasmonic. This is called an antenna reactor system, but a similar concept. You are separating hole and electron, and if that is really possible, then possibly you will get a good catalytic activity, right? So what we did then, we took the black gold, loaded with a nickel salt, reduced it by a reducing agent, and we got a black gold loaded with nickel, right? So this is a typical synthesis. You prepare a black gold with cycle by cycle, load the nickel nitrate, reduced by sodium borohydride, followed by a H2 reduction to get really a nickel zero. And obviously the TM images don't show you the nickel versus gold separation because they have similar Z contrast. But if you do elemental mapping, you can see wherever there is gold, there is a nickel, right? So that indicates that the nickel is nicely coated onto the gold surface, and that's what we wanted. We wanted electron to go from gold to nickel, so they need to be in good touch with each other. Then these are some of the basic characterization. You can see even after loading nickel, the light absorption doesn't change much. Oxidation state wise, nickel is actually in zero state because we did this CO titration and we found these signals, which is for the nickel zero with some amount of nickel 2 plus. We also carried out the DETD, this finite difference time domain simulation. This gives you because of the surface polarization now, because of the SPR, and because of these dipoles moving with the electric field motion, you create huge amount of electric field around the nanoparticle surface, right? And that field could be very, very high. You can see 824 volt versus 23 volt per meter, and you can see it creates some sort of a hotspot. The electric field gets concentrated between the two active sites, between the two nickel nanoparticles, and that concentrated electric field, we call them a hotspot, electrical hotspot. Now you imagine if your reactor, there's a CO2 or hydrogen, if they go in these hotspot, because of this polarizing electric field, they will get pulled, they will get bent, stretched, and that will again allow you to activate those molecules and reduce the activation energy. So this is additional advantage of using the LSPR to carry out the photocatalysis. So how do we do the catalysis? So we do a gas phase catalysis. So you have this Asahi xenon lamp as a light source, which is more like a sun in the lab. you have the small reactor here where we light focuses onto the solid powder. You can see a solid powder here, the black color powder here, and the GC allows you to monitor the product form. So in cartoon, see here you will have the catalyst, light comes from the top, so your black gold is exposed with the light. You mix the gases, in this case CO2 plus hydrogen, pass through the catalyst which is already exposed with under exposure with light, and whatever the product it forms, if it is a gas, you will monitor by the gas chromatography. If there is a liquid, we trap and do a GCMS RMR. So this is the basic way of doing, and this is the flow reactor is happening with time. Now look at the results. So we carried out these catalysis at different intensities, light intensities, right? So these are at a different light intensity. So let us look at only just one data to simplify. This last data, which is 2.77 watt centimeter square. This is done at 2.77 watt per centimeter square. And now look at the activity, look at the rate of the reaction. It is around 2500, and look at the unit, millimole per gram and per hour. So that was 1.75 micromole in 6 hours, versus now you have 2500 millimole, that too in a flow, So you can see a dramatic increase in the rate of a reaction by simply designing a catalyst, a gold and a nickel antenna and reactor, which separates the electron, and then you can use those electrons to carry out CO reduction. Excellent selectivity towards CO, and also very stable. You can see stable up to, we tested up to 100 hours, and you can see within the error bar, they are very stable. And looking at this flat line, ideally it should be stable for a year or so. We also tested, compare our catalyst for range of other best reported catalyst system, plasmonic as well as semiconducting, and our catalyst was 182 times higher at that time in 2023 as compared to any photocatalytic system for this reaction. Only challenge is in our work as well as all the work that is reported in the literature, we use a high powered sun. It's not a one sun. You need at least minimum 10 suns of a power, right? And that makes the process challenging. So now there are two ways to resolve this. One is I develop a new material which works at a one sun and get me the same activity. This is exactly what my group is trying to do now, designing a new material which will give me the same number at one sun. However, even if that is not possible, there are ways to concentrate the solar light. There are these mirrors which can concentrate solar light up to 30-40 suns, and that is also what we are trying to work. We are trying to work with one of the industry to develop such a reactor which can use directly this material and concentrate the light. Okay, so now I will take 5 minutes to explain the mechanism part, and then maybe another 10 minutes to 8 minutes to give you some other work that we do. So I told you that once the LSPR is broken, all those photons were damped onto the surface of the nanoparticle, and you generate these hot electrons, and these hot electrons injected into the CO2, and you carry out the reaction. So it's ideally hot electron mediated reaction. However, there is a debate in this field, and there are a group of scientists who says this happens, the lifetime of these electrons are too short that it will never go to the CO2, but they will come back, they will relax, and they will go under electron-phonon coupling, and it creates this localized heat onto the surface, and everything is all about the localized thermal heating. So the good number that we see is thermal heating and not a hot electron non-thermal process. Now in order to answer that, what we did, say when we expose the black gold with this particular light intensity, which was 2.77 bar, the temperature of the black gold that increases was 223 degrees Celsius, right, by exposing the light onto the black. So when we carried out the reaction at 223 degrees Celsius without light, in dark but heated by some heater, the activity is zero, right? Zero in the sense not detected in the GC, there could be some ppm. So that, let us say 0 for now. So at 223 in dark, zero activity. At 223 in light, activity is 2500. So this experiment clearly says that it has to be light. It cannot, because it is not working in dark, right? But then the counter argument is, how did I measure the temperature? So we measure the temperature by inserting the thermocouple directly into the black gold powder. That's the best a chemist can do. Or you can use the IR camera, and we get a similar temperature, 223 degrees Celsius. But the real temperature of the nano surfaces, because of this plasmonic damping, could be not plasmonic damping, but the electron phonon coupling could be very high, maybe 1000 degrees Celsius, and maybe If we do that at that temperature, possibly you get the same activity. Obviously, you cannot heat this at 1000 degrees Celsius because it will just melt. It's a metallic nanoparticle. Then how do we answer? We also use the other technique called Raman thermometry. We all know that whenever you heat some surface, you get your population in a higher vibrational state will be higher. So that means you will get a more anti-Stokes lines versus the Stokes lines. And Raman thermometry says by taking the ratios of anti-Stokes and Stokes lines, you can get temperature T. We use this technique, and the temperature that we obtain is even less than what we observe physically, which is 150 degrees Celsius. Clearly, this is not also a correct way of measuring the surface temperature. But then other experiment that we did is, you take a black gold and add more photons. If you add more photons, what will happen? You generate more hot electrons. And if it is really a hot electron mediated reaction, then more hot electrons means your rate will also increase in the same way. So now you see in this particular plot, we increase the light intensity from 1.7 to 2.7 watt per centimeter square. So I'm putting more photons. And now you see there is a linear relationship. So this is the production rate. You can see a linear or a super linear relationship between the light intensity and the CO production rate, clearly indicating that it is a hot electron mediated reaction. We also measure the activation energy barrier experimentally, and you can see in light it's 0.22 eV versus in dark it's 0.68 eV. So clearly, why will the activation energy barrier reduces? So because of the polarizing electric field, right? And that you can clearly see in the LSPR, and this again in activation energy barrier measurement, and it clearly indicate that it has to be the hot electron mediated and not a heat. We carried out several other experiments. I will skip it to save the time, and you can see KIE, kinetic isotopic effect, also says that it is a light mediated reaction. We also try to understand the molecular mechanism, how the CO2 sits onto the nickel and how it separates to the product. And you can see here CO2 sits onto the nickel sits onto the CO2. CO2 decomposes, it is a direct decomposition or direct dissociation into carbon monoxide and oxygen. Carbon monoxide, because of the surface potential is surged because of this polarizing electric field, that CO dissolves and your product is CO, and then oxygen reacts with hydrogen, you get water, and your nickel site is free. So this we studied using the in situ drips measurement. Right. So this was all about plasmonic black gold nickel as a catalyst, photocatalyst to convert CO2 into these three chemicals. I will take 3-4 more minutes to just present some other work quickly and briefly, just to give you overall what we do in our lab. So we also extended this plasmonic black gold for some other reaction like acetylene to ethylene, right? C triple bond C to C double bond C without going to C single bond C. It's a very challenging reaction. You cannot stop at C double bond C in general. Whenever you do a reduction, you will always try to go to the single bond C. But by tuning the active site, in this case RUPT, as well as the surface potential by the LSPR of the black gold, we showed that as soon as acetylene converts into ethylene, it dissolves and doesn't stay onto the surface, and that's why there is no chance of ethylene to again hydrogenize to ethane, and that's how we were able to get more than 99% selectivity for ethane. And this was one of the first example where we showed the surface potential tuning by the LSPR. Another challenge in this field was making the black gold itself. In general, it used to take us around 1 week to make them, 5 days to make them. But now Rishi and Sushma came up with a nice process which says now you can do it in a 1 day, ideally 5 hours, and this is a one pot, and we have already published, and if you are interested, you can also make it in your lab. It's extremely simple now to make these black gold in your lab. One can ask why gold is very expensive, why are you using gold, why can't you use something else? So we also asked this question, and we showed that you can also use nickel nitride nanosheets which are terminated with a hydroxy, and they also work as a CO2 reduction using plasmonics. Obviously, if you compare the stability of this with the gold, gold is always stable. That's the beauty of the gold. They are extremely stable, and although they are expensive, we use a very small amount of it and they are stable. Let us say you use a small amount, get a great production rate, and they are stable for the year. So even if it is expensive, the overall process will be sustainable. Overall process will be economic. So that's why we should generally not worry about so-called the noble versus non-noble method. That's what we believe. Okay, other than the photocatalysis, our group also, so we are divided into two parts, photo and thermal. So photo is more a big dream thing, so it will take some time to really make it to the commercial scale. But thermal catalysis is something that's already happening in a commercial scale. So we asked this question that how do we improve the catalytic system thermal catalytic system to carry out the CO2 reduction again, and where we showed that metal was one of the problems, because once you put a metal on the silica, these metal nanoparticles try to oxidize, try to sinter. When you heat them at a higher temperature or expose them to the environment, they deactivate. So we said, okay, let us not use the metal. So if not use the metal, then what do I do to activate CO2 and hydrogen gas? So we showed that by creating the defects, which is like oxygen vacancies, oxygen radical and a silicon radical, and they need to be together. If they are separate, nothing is happening. When they are together, they cooperatively work, activate CO2, dissociate hydrogen, and convert CO2 to methane. This is what we showed in this work. However, since there was no metal, although it was stable and showed a good activity, but not the great activity, not the activity that you required to make it commercially valuable. So then we asked this question that, okay, defect alone is not going to do it. So now let us combine the defect with the metal. And we know metal has a problem in terms of oxidation and sintering. So can I use these defects and create some sort of a strong interaction of the surface with the metal? It's called a strong metal support interaction. You have a support, in this case, it's a silica coated with a TiO2. You create oxygen vacancies in the TiO2. So now you have a very reactive surface. And when you put the copper side, which is very active as such, its activity is also interesting, because now the electron density is pulled towards the surface, as well as you have the defects giving the electron density to stabilize the copper onto the surface, and that allowed us to get us very high activity, around 5,000 millimole per gram, and more importantly 200 hours of stability, at least 200. We tested up to 200, it will surely a higher time. And copper, which is known to be unstable, now is not only stable but also active. But again, this is not a number that industry needs. Industry needs 50,000 millimole. What we have is 5,000. It took us around 9 years or something to get to 5,000 from, say, 5 millimole or something. Now objective was to get to 50,000 millimole, 10 times more. What do? I already changed the surfaces. I already used the defects. I already played with the metal sides. None of that gave us the number that we need. So then we came up, especially the Charlie Singhvi, one of my PhD students, came up with the idea that, okay, now let us not use one metal, because there you're not able to tune the metallic. Is always a binding strength of the reactant and the intermediate onto the surface, and one metal and the defects alone is not going to tune it. So we use these three metal and their electronic dynamics, as well as the defect dynamics, that allowed us to come up with a active site which has a potential perfectly optimized for CO2 activation, perfectly optimized for CO disruption, and that gave us a number very close to 50,000 millimole per gram. This is very recent work, and the number is so good that we already started upscaling this work. Even before publication, we had a MOU with BPC and Noida. They have the expertise of upscaling it. So we are already in a state of upscaling, and hopefully, if the upscaling works, possibly this could be a process which is commercially viable. We also put some amount of efforts in a plastic degradation, waste plastic degradation, and Ian showed that you can use these, you can make these salt acid, which are mesopores, and they can degrade waste plastic into fuel. We are also making lots of attempt to take some of our processes into a commercial scale. This is another process which we were working with Adani, and that's the goal of our group is not only do a fundamental science and keep publishing the papers, but one day at least one or two of our processes should see industry, should be there in the industry and help our society, and we are very dedicated and motivated to achieve that. Although it's very challenging in Indian ecosystem, extremely challenging in Indian ecosystem, but we're tackling all of those red tape and trying to achieve that. With that, I like to conclude. I showed you these black gold nickel. So black gold acts as an antenna, take all the photon reactor, which is the nickel, acts as a catalytic site where the reaction happens with the CO2 and hydrogen. And we also showed you quickly another very recent work where we use this defect-rich ceria and nickel copper zinc to get you the CO2 conversion, the CO production rate up to 50,000, nearly 50,000 millimole per gram. And we're trying to see where this there are several unanswered fundamental questions that we are also trying to find a collaboration and understand. With that, again, I like to thank the organizing committee, Bhaskar, Professor Mani, for giving me this opportunity to give the presentation. this very respected memorial lecture. It's my honor, and I'd like to thank you everyone for listening to me, and more than happy to take some questions.
Okay. Thank you very much, Vivek.
Thanks.
Yeah. Yeah. So I think people can raise the hand which are on virtual, and I don't know how to communicate people which are in the auditorium. Yeah, someone can coordinate from auditorium questions. Any students, anybody has questions in the auditorium, please do ask. Anyone on virtual platform, please raise your hand.
For a BSc student, if you want to ask in Marathi, मला आता
Yeah, yeah.
मराठीमध्ये सुद्धा उत्तर देता येईल.
हा, मराठीमध्ये सुद्धा विचारू शकता
विचारू
तुम्ही.
शकता. मला आता थोडं जास्त आवड लागलं मराठीमध्ये बोलायला, मराठीत
Hello, sir.
हा, please go ahead.
Nice lecture, sir. I have one question regarding the electrochemical reduction of CO2. We have observed a large number of products or less selectivity. Have you observed same with photocatalytic? Because as the wavelength has been changed with the nanomaterials, particularly at a single nanomaterial, that will be okay for that particular wavelength. But when we compare or consider both like gold and nickel, at that time the wavelength has been changed due to interface of that particular material. So at that time you will get a particular selectivity or varying with selectivity with varying the absorbance of that particular light.
Yes, yes. I think that's very exciting question. Thanks for that. So, see the difference between the semiconductor-based photocatalysis versus plasmonic photocatalysis is the semiconductor is always say one photon with a direct electron excitation. Right? You put the photon, you get the electron, and that's level independent. But here it's the other way around. You have a broadband light absorption, and where almost all the photons get collected together and damped down to the surface, and then that entire energy is used to generate hot electrons of a different energy. So there will not be a direct relations of the wavelength with the selectivity or the yield. Ideally we see a more relationship with the intensity of the light, because you put more photons, you generate more hot electrons, and you carry out the reaction. But this is happening in the case of a black hole because it's a very broad band. But if I use a plasmonic, conventional plasmonic with a different wavelength of the light, then there is this theory that there is a possibility that some nanoparticle can activate some modes of the molecule, and you can then have a reaction at that particular functional group, and that can tune your selectivity, right? So it's very different than a typical photocatalyst, as well as obviously very different from the electrocatalysis, right? There the mechanism is completely different.
Okay, Professor Vivek, is Bhaskar here.
Yes, Bhaskar.
Okay, if you are talking about the plasmonic nanoparticles, and especially if you are making by the colloidal approach, the possibility to get a polydispersity is more.
Yes.
So that will help us to get the more absorbance. If the variable band structure is, the gap is there, band gap is there, you can get the more absorbance. In that case, is possibility to get a higher yield of conversion or no? Or that will affect on the selectivity?
Point. So when we started the synthesis, we don't wanted to have any heterogeneity in the particle size. Then you can really directly correlate the distance between the particle versus the activity. But even after spending a year, we never able to make a such a heterogeneity. You always have heterogeneity because it's a silica sphere, right? So the particle which is sitting at the tip of the fireball will get a more gold atom versus the particle which is sitting at the core of the silica sphere. So you will always have the kinetic difference in the growth stage, and you always get a heterogeneity. And that obviously, that's what I also showed you in my slide. So the heterogeneity in the particle also help in getting the broadband light harvested. However, the contribution of the heterogeneity is not that great. If you only mix different size of the particle, you don't get a broadband light absorption. You will never. You will some lambda max, but it's only the plasmonic coupling when you get a broadband light absorption, and the heterogeneity will add into, say, a 10% or something like that.
Yeah. Any more questions? Anyone from auditorium?
Hello. Yeah, please go ahead. Am I audible?
Yes, yes, you are very much.
Yeah, this is a general question and this is for student purpose. As your last slide is related to laboratory to industry. Like that way, I want to ask question from Amravati to TIFR via France, USA and Korea. Guide to our students because in hall more than 140 postgraduate students, they are pursuing MSc and some students are pursuing PhD degree. Over to you, sir.
Yeah, thank you. Thank you. It was very nice of you. Yeah, thank you very much. Thank you. Anyone else? Okay, I think we were just quick question on this. You were saying it like, you have to really use high power of sunlight.
Yes.
And then increase the temperature, right?
Yeah.
How are you going to really address that? Because one sun, and then when you are using a low intensity one sunlight, you see the reduction in activity, right?
Yes.
To the thing to enhance the.
There are two ways. So see why there is a heating. There is a heating because there is a more electron phonon coupling. So now I need to design a material, right, using by playing with the dielectric constant of the material that I'm going to make, such that the electron phonon coupling doesn't happen and all the electron goes to zero. It's more like the lifetime of the electron as well as the dielectric function of the material. That's more a fundamental design and it takes time to design it. But otherwise, also you can use the solar panels, solar concentrator, and it will add. You will also have a heat. So reaction anyway happens with the heat at certain temperature, as well as the light mediated electrons, and you will combine effect. So that's what we're trying to do now.
Thank you. Any other comment? Any other questions? I don't see anyone hands up in virtual as well as in. I don't see anyone in auditorium. In that case, let me also take this opportunity again. Thank you very much for this excellent lecture. I also thank organizer, especially Bhaskar, Professor Mani and Professor Shinte for giving me this opportunity to prepare this session. I hand over back to the organizer.
Thank you, sir. Thank you, Paul Shettiwar sir and Satish Patil sir for such a nice, wonderful, knowledgeable lecture. This lecture has been a remarkable journey covering all the aspects of nanomaterials and their applications. Thank you once again, sir. Now we will move towards the second session of this series. Let us commence second session of this series. So I now request Professor Babu Shinte sir to introduce Chairperson M.K. Lande sir.
Thank you, Bhosle ma'am. It's a pleasure and honor to me to introduce one of our senior colleague, Professor M.K. Lande sir. He is having a vast teaching and research experience of more than 27 years. His expertise in teaching group theory, symmetry, organotransition metal chemistry, and many more. His area of research is heterogeneous catalysis, particularly synthesis, characterization, and applications of natural zeolites as well as the synthetic zeolites. Not only this, but also recently he has started working on some DFT study also. So far, he has published more than 125 research articles in the journals of international reports. Having H index is of more than 30. Total citations are more than 3,000 with I-10 index of 67. So far, he has guided 15 research scholars for PhD degree, and currently 8 students are working under his supervision. Now, may I invite Professor Lande sir to chair this particular session of 5th Professor D.B.Ingle Memorial Lecture Series. Over to you, sir.
Thank you, Dr. Bapu Singte sirs. I would like to introduce today's resource person, Professor Bhaskar Sate sirs. Respected my teachers, Professor M.S. Singare sir, Professor R.A. Mane sir, Professor A.W. Rajbose sir, Professor Y.S. Deshpande sir, Professor Somanshi sir, D.B. Mane sir from Umarga, Rajita Ingle madam from Devgiri College, Aurangabad, and Head Department of Chemistry, Dr. H.G. Shankarwar sir, Senior Professor, Dr. Anjali Rajboj madam, Senior Professor, Dr. Suresh Gaikwad sir, Bapu Singte sir, and postgraduates and research students. I am here to introduce today's resource person, Professor Bhaskar Sate sir. He has completed post-graduation from this department with physical chemistry specialization and qualified CSIR NET GRF examination in the year of 2004 and completed his PhD works at National Chemical Laboratory, Pune. And after that, he joined as a faculty member to this department in the year 2008. He has received Fulbright Nehru Postdoctoral Research Fellowship Award and worked as a postdoctoral research fellow at Rutgers, the State University, New Jersey, USA, for 2 years. He has more than 16-year teaching and research experience. Under his able guidance, 8 students have awarded PhD degree and 8 students are working under his able guidance for PhD works. His research area are nanoscience and technology, inorganic material as a metal, metal oxide, carbon nanotubes, fullerene, graphene and their heterostructures, fuel cell-based electrocatalytic reaction, sensor technology, electrochemical water splitting, and biomass conversion reaction. Professor Bhaskar has published more than 110 research papers in national and international reputed journals, also published 2 patents with more than 4,000 citations with H-index 30. He has published 1 book and 7 chapters. He has recognized as a world top 2% scientist by Stanford University ranking for the year 2020, 21, 22, 23. Based on his excellent research contribution, he has received more than 2.5 crores rupees under major research project funded by DST, DST Fast Track, DST SERB, DAE BRNS, DST SHRI. Professor Bhaskar Sate sir has received several awards, recognition as a Fulbright Fellow already in the year of 2013 by United States Indian Educational Foundation, Young Scientist Award 2013 under Fast Track Scheme, DST SERB New Delhi, Young Scientist Research Award 2015 from DAE BRNS Mumbai, Young Association Maharashtra Academy of Science 2018, Fellow of Maharashtra Academy of Science 2021. He is an active life member of Indian Society for Electroanalytical Chemistry of India, Executive Committee member, Material Research Society of India, Electron Microscope Society of India, Electrochemical Society of India, American Chemical Society of India, USA, Society of Material Chemistry. He is also editorial member of various journals and reviewer of the various journals. Professor Bhaskar has nominated as a BOS member in chemistry, Deccan Education Society, Ferguson College, Pune, Rajarshi Shahu Mahavidyalaya, Latur, Department of Nanoscience and Technology of this university, Department of Forensic Science of this university. He is also RRC committee members in Basic and Applied Science, MGM University, Chhatrapati Sambhajinagar. He is also nominated as a member of Technical Committee, Pradhan Mantri Upchar Shiksha Abhiyan, PM Usha Cell. Professor Bhaskar is also elected Senate member of this university. Professor Bhaskar is presently shouldering the responsibilities of Director, Center for International Relations, Coordinator of Department of Forensic Science, and Head Department of Nanotechnology of this university. With this brief introduction, I may request Professor Bhaskar Sate sir, please deliver lectures on nanotechnology. Thank you very much.
Good afternoon, one and all. Thanks to Lande sir for nice introduction. First of all, I would like to thank organizer, my teachers, for giving me an opportunity to be a part of this series. Why I am considering this as an honor for me? Reason that since last 5 years we are listening very eminent personalities from different fields who have the national and international recognition in chemistry. So for this, I don't know why they given me as an opportunity, but I will try my level best, because again, the presenting in front of teacher is a big task. I will try my level best in next 1 hour. Again, for students, I am in different role today. I am a resource person of this series. So, as a part of camera. थांब. काय गडबड आहे?
फुल स्क्रीन घेऊन ते त्यांच्याकडे आपल्याकडे हे आता ऑनलाईन सर याच्यापेक्षा करा सर, हे 100% करा सर, मी सांगतो तुम्हाला डिस्कस करा. हां म्हणजे आहे ना, हे 100% करा सर. हां बस झाले सर. आता तुम्ही हे करा सर, स्लाईड शो करा.
स्क्रीन यायला पाहिजे ना
सर तेवढी नाही येणार त्याच्यावर.
तेवढी येते दररोज, तिच्यावरच येते.
आता सिस्टीम त्याला लावली सर, ती त्यांच्याकडे येते.
पेन ड्राइव लगाएंगे उधर उधर लगाएंगे.
नेट लगाना पड़ेगा. नहीं तुरंत देखिए.
Okay. Today for this session, actually the theme is decided by the organizer is to arrange the lectures on sustainable development, which is especially in line with the energy and environment. Since last 1.5 hours, we have listening the work which has done by the Polshetivar, Professor Polshetivar in TIFR, which is on CO2 reduction. In line with that, I'll be talking on hydrogen generation. The question comes, why hydrogen and how the material contributing to that? And as a chemist, what is our role? So as a part of that, outline of my talk is, first I will give the general introduction about how the chemistry together with the physics and engineering will contribute towards the development of new materials. Then there are certain lacunas, we can say, or key steps where us need to work. That is actually challenge in front of you student as a budding scientist. So that in line with the nanotechnology, there are some limitations belongs to nanotechnology that also I will highlight at some place. So then how these new materials contribute towards resolving some societal issues. Earlier, the issues were different. We used to say Anna Vastra Nivara, right? So, but that has extensively changed, and the global challenges or the issues has come up with the serious issues of energy, and energy is in connection with the environment. Because if you are talking about the contribution of new field as a nanotechnology, nanotechnology is by the great words, the great word by the Richard Smalley, he talked that nanotechnology holds the answer to the extent there are answers to most of our pressing materials needs in energy, health, communication, transportation, food, water, where this new field will contribute. Right, next. So if you are talking about as a chemist, what is our role? As we know, if you shift from single atom to the molecule, like a simplest molecule, like a diatomic molecule, if you assemble two atoms together will become a molecule. The molecule is having extensively different properties than the individuals. So because of that, the properties automatically changes. And if the properties are changing, its application will get changed. Utility will get changed. We are curious about the development of new materials and its utility for different applications to get a solution for the recent problems. Next one. So then if you are talking about the materials and its length scale, if you start from the fundamental unit, so few atoms together will become a particle. And its particle is having the dimension is smallest possible in a nano. Now the technology is reached to the level where we can see in one single atom. Right, and the atoms are having the different properties than the molecules. Unfortunately, whatever may be the textbook chemistry or physics or the engineering is there, that belongs to the bulk material. But the big difference is there, what is at the small scale. So then, and again, if you are comparing the simplicity with the complexity, as far as the count of number of atoms involved in the material is concerned, it is a big change. Even our quantum mechanics says the solution for the single particle, like one proton in one nuclei, right? So its difficulty will get increased if you shift from the higher protons, like 2 proton, 3 proton systems. So that complexity is more if you go toward the bigger particles. And unfortunately, you cannot justify why this material is showing the this particular performance. But that is very simple if you go toward the lower dimension. Means identity of atom is there in periodic properties of a single atoms are there as such. But that properties will change if the number of atoms comes together. So what I want to convey here, the complexity when it is getting increased, the materials we can control by their number and we can utilize that change in property for certain applications. Next one. So as the number counts, number matters. So if you are going toward the lower possible size, the physical and chemical properties are changes extensively. Especially the majority of physical properties has changed, like 100% physical properties will get changed, but like a 30-40% chemical properties also get changed if you go toward the lower dimension. Even though the metals like a gold or the silver who's having the melting point around 1000 or above that will be in a liquid form if you go toward the 3 or 4 nanometer size. So it's a big difference. If they are having the golden color is well known for us for the gold, the color will become like a wine red or some like a purple or pink if you go toward the lower dimension. Depends on the size. That I will show you how it is. But again, already we have listen on last class, last lecture, where how the plasmonic properties are there. So the plasmonic properties are dominant if you go toward the lower dimension, especially for the metal nanoparticles. So again, the single electron transfer properties. Go back. So see here, because of this cartoon says it's possible to jump individual electrons from one atoms to earlier. See the earlier electronics, TVs or mobiles or laptops or any equipment is like electronic equipment where we used to see the dimensions are big. The electronic circuits inside the equipment are having the like the dimensions are more like a bigger. So even though few electrons are more enough to run that equipment or to operate that equipment, unnecessary because of the big wiring, the energy loss is there. So battery performance comes down. So nowadays you see our mobile is equivalent to one computer, equivalent to one studio, right? We can see any site we can open, you can see that at the time 3-4 different apps you can work on that, right? So even though that is possible to work for a day on that same battery, the reason why energy loss is controlled. How to control it? If the single electron transfer is more enough to get a signal from somebody, why to waste for the 100 or 200 electrons? So that becomes possible. So that change makes energy storage or energy utilization management. So in that sense, this nanotechnology is contributed more in electronics that is visible. In market also, if you buy a mobile this year, same model we cannot, we cannot sell in next year because the price of fresh mobile of same will be reduced or the new version will come, new facilities will be there in that case, right? So this big difference is that contribution goes to the technology, right? So this again the physical properties is melting point and the reduction potential and all these things are already there. So if you are talking about the plasmonic properties, very first in 1857, Michael Faraday, he has accidentally observed that the colloidal gold nanoparticle, and it theoretically had supported by the my theory in 1908, and combinedly they come out with this platform of like a creation of a surface plasma and how it creates a surface charge and how that charge next one is associated with the interaction with the electromagnetic radiation. So that collective electrons which are coming on the surface that interact with the light and the oscillation with respect to nuclear positive charge, nuclear positive charge will show the absorbance. And that absorbance depends on what is the size, how many electrons are there, because size, if the size is more, electrons will go away from the positive charge and electrostatic force of attraction will be less. So easily they will oscillate with by the cost of interaction with the electromagnetic radiations. That is not possible for the smaller particles where the electrons are very close to the nuclear positive charge, and that hold requires more energy to take away that electrons from the surface. So that possibility is responsible, or that the reason why we are observing even gold is having the golden color, we are having the shade of colors. Next one. So this is the actual data I am presenting here. Next one. So again, the electronic property, how it changes, even though we used to say the copper, silver, gold, aluminum, tungsten, these are the metals. Electrons are there on the surface, and that plasmonic electrons always try to run by the cost of either temperature, electricity, or light. So, but if you go toward the lower size, you start with the fundamental single atom. When another atom, if allow atoms to interact with the same family member like another atom, so two atoms overlap their atomic orbital and molecular orbital forms. So the molecular orbital, then automatically one will go down, another will go up, will become a gap. Even though we are talking about the copper, we have the particular gap, and it becomes a semiconducting, like that metal, we are shifted to the semiconductor. So that, or even the two atoms we are talking about, that will be like a gap is huge, like insulator. So our interest is here. Is it possible to control the number of atoms to change the properties from the metal to the semiconductor? Because we want electricity, or we want energy transfer or electron transfer in a semiconductor way. So that is possible. How it is possible? By control the number of atoms. We need to put a serious efforts to control the surface, to control its growth, to become a higher particle, or so bigger particles, right? So next one. So this is an example of how the solid grows, and this band structure means, like if you are talking about this is the antibonding, or we used to say the conduction band, this will be like shifting from here to here to here to here to here, and this will grow from here to here to here to here, will reach at this point. So, right? So this big difference is there, which represents the how the number of atoms decides the property. Here we have the insulator, here we have the semiconductor, and that side we have the metals, even the same element we are taken. Next one. So this is the actual example of gold with respect to count number of atoms I am talking about. If you have the gold in a 30 number of atoms, we have the huge gap. And if you go toward if you are not having the control during the synthesis, if the gold is having around 225, is like a 0.2 volt gap, or beyond this, it means if you are not able to control the gold nanoparticle size, like a 5 to 6 nanometer, is of no use. Even though we used to talk, we have made the nanoparticles, but the size is not below certain limit, especially for the gold I am talking. So we can say is of no use, like it works like a bulk, we can say. Next one. So I am very much interested here. So why it is? Because whatever may be the catalytic or electrocatalytic, photocatalytic reactions which were operating, that will be on a surface. So surface is very important. So especially if you are talking about the bulk material, only skin is accessible for the element, any species to come, like a reactant species to come and interact, and followed by their polarization, and it's converted into the product. So this possibility is only, this responsibility has taken only by the skin. So the bulk material, or the material which is not exposed, is of no use. So then question comes, then why to keep it there? Because that increases the value, or that increases the cost of a process. So then technology, nanotechnology will help us to take out that material. We can make a powder. You've taken an example of cement. I used to give the cement example always. If you are taking the stone and its fine powder as a cement, if you are comparing these two, you will see the difference. The properties are different. The holding capacity is not with a stone, that capacity is with a cement. And the cement is always ready to hold these two bricks or even some internal particles together. And that is because of its surface. And it is that is unstable. It is against thermodynamics. You cannot keep that for a longer time. Cement of no use after 2 to 3 months. Am I right? So this is because the surface atoms becomes more active. Here especially if your 3 nanometer particle is there, exposed portion is about 50% or the more than that. If we have the particle, if you are not able to control its size shifted from 3 to like 10 nanometer, so this surface area will get reduced. To increase the surface area, we need to put some additional efforts to keep their size maintained for a longer time. So this is actually useful for the means like heterogeneous electron transfer processes. Here again, by the size or by the conjugation with the another nucleophiles, electrode potential also variable. We cannot say this particular metal, like we have taken the silver electrode and silver electrode is performing with the same potential. If you have the lower different dimensions or the which is surface impacted by some other nucleophile, right? So it contributes towards the change in potential also. Next one. So then question comes, how to build, how to fabricate this nanostructure. There are 2 different ways. Always physicists give the preference for this one, or to take a bulk material and try to make the fine powder by cutting it into smaller and smaller. But as a chemist, we have the controlled synthesis approach where the reactant is in our hand, how much we are taking depends on the concentration, and we have the control that we can do by our own. Next one. So as far as if you are shifting from the general properties to the material, if you are talking about the most contributed element in a periodic table is the carbon. It's in inorganic chemistry, is in a biomaterials, or even in life, also in drugs also, right? But especially if you are talking about the inorganic material, the contribution of this carbon and carbon resources is more, right? So here before 1980, only 2 allotropic forms of carbon were there. Like one is graphite, another is diamond. And we know that their properties are extensively different. There are 2 ends, you can say. Graphite is black in color. Diamond people are using as a jewelry and so on. Even the electrical properties are different. One is insulator, another is the highly conductor. So, but the chemistry has changed. If you have the control number of carbon atoms, that has come after the, like in 1981, Richard Smalley got Nobel Prize on 1996 on the discovery of C60, and the further elongated form of C60 is C70, and the extended form of the carbon nanotube, that is he got a Nobel Prize again for the discovery of the hair-like structure of halo hair-like structure of the carbon, that is the carbon nanotube, and that was till 2008. 2008, another allotropic form of carbon has come, that is a graphene. That graphene we can make by cutting, systematically cutting the tube, as one sheet will come out, or take out one sheet, like one page from the graphite bunch. Graphite is nothing but a bunch of graphenes together, you can say. The sheet of graphenes together is nothing but a graphite. So if you systematically remove the outer layer of a graphite as a one skin, we can say is nothing but a graphene. And why the graphene is the efficient material, or we can say is catch the major market of the material science. Reason behind is having the one sp2 carbon, where the one additional electron is there. That electron is always contribute toward the different properties, right? So this is the actual the contribution of carbon toward the development of new material is there. And the reason behind this is the having the complexity capacity. नाही तू जॉईन करत
होतंय सर ते फक्त काय नेटवर्क थोडं
त्याचं हे कुठं आहे रे So now we will move towards how this material contributes to the resolve certain issues where the society is facing. As we said, the sequence has changed these days. The energy has become a big challenge in front of us. Reason is very simple, because if you want to improve ourselves, we have to come in a competition, am I right? So if you are talking about the country, is the same issue. Globally, if you want to control, we have a certain fields where growth should be there, where the industrialization should grow, transportation should fast, right? So then we can get a decision very fast. If you want to go to Delhi and come with some document, and immediately if you want to implement, we have to give the preference to the air transportation instead of bus or the train, right? So it will take a week or more than that. So that where the energy consumption becomes more. And unfortunately, we don't have the renewable resources which are sufficient. We have the dependency on the fossil fuels. So the burning of fossil fuels, over burning of these fossil fuels will contribute diversely in the environment. And the seasons are getting changed. We have listened in earlier talk that how the importance means how the how much important is there to reduce the carbon dioxide content from the environment. Naturally, if you are talking about the carbon dioxide content is below 1%, below that in 0.1 or 0.2%. So that becomes like a 70-80% at a metro places in a metro cities. Like a place like in a Gulmandi or the railway station or the bus stop where the content is high. And unfortunately, that is not good for like even health. So the recent findings on carbon dioxide research says the gravitational force which is acting on the carbon dioxide holds the carbon dioxide in a zone of like 5 to 7 feet. And so the content becomes, if it is 80% content, just imagine where the oxygen comes in that zone. So then we'll feel the uneasy or uncomfortable in such type of metro places. That will be for the small kids is not good, or in even the senior citizens will feel the uneasy in cloudy places, right? So this is another phase of CO2 I am saying here, and the actual well-defined contribution of carbon dioxide is to change the global warming. Environmental issue, even though is not we cannot say is a toxic, is indirectly is become a toxic to the is environment, also for the human resource, right? So then we need to work on that, how to manage the, how to control. Reduction is not a reduce the energy resources is not a solution, I can say, but we can manage, we can find out some alternative, we can work on a fossil fuel somewhere at the corner, and we'll play with, we'll manage with their pollution and all these things, and that energy source we can transfer, distribute as we need, right? So that, now it's working actually. तू करून काय back. this carbon dioxide emission is contributing toward the global warming, and we have seen the both ends of this galaxies started burning, and the ice melted is the satellite view is saying the ice content is coming down, is started melting and all, right? You might have seen the news, scientific news, where the some means like life for the earth is not much. Some one day will come, the earth's surface will cover by water and all this thing, right? So, but that is having the this particular background for this. Next one. Next one. So, if we are talking about the energy and its current status, energy is one of the grand challenge, of course, and is, but unfortunately it is not monolithic. It depends on n number of issues. Its supply issue is there, demand issue is there, conservation, application, scale up, location, right? Fossil fuels will have still, we don't have the solution alternative for the fossil fuels, but we need to work on that to go for the renewable resources, but renewables are growing. Unfortunately, the outcome which is coming from that is not sufficient, right? So you might have seen the how even the for one seat in an aeroplane, how much carbon dioxide will get emitted. That your ticket is coming these days, as like a cigarette pocket. Warning is there. Same warning will be there if you are just as a sake of what you can say the just as a passion, if you are going with the air, how much CO2 because of your one trip from Aurangabad to Delhi is contributing, that count is there, right? So this much awareness is there, but unfortunately we don't have the alternative for that, right? So then the question comes, it's better to shift from the fossil fuels to the, because see, if your fossil fuel is nothing but, as a chemist we know, the fossil fuel is nothing but hydrocarbons. The carbon and hydrogens together. So if the carbon is contributing divertly to the environment in the form of carbon dioxide, why not to avoid it? And it's better to shift to the hydrogen. So in that point of view, the hydrogen is good. Why it is? If you are talking about the energy density is 38 kilowatt per kg, and compared to the resources which we are using is much higher, right? And again, another beauty of this is output is there is no emission of carbon dioxide in the environment, and that hydrogen we can use for a different purposes, and this through the electrochemical transformation, because here the hydrogen we can use as an anode, and we can do the electron transfer, and as a result of that we'll convert this fuel to the electricity, right? So but as far as the hydrogen production is concerned, the global content where the 48% people are doing collecting the hydrogen from the dry distillation of the fossil fuels or the gasolines, where the 48% hydrogen is collected, 30% from the oils, 18% from the coal, and 4% only from the electrolysis of water, where we have the more than 80% content on the earth's surface, right? So if you are talking about the hydrogen from water, is nothing but a very simple electrolysis process. We have anode and cathode, and if you are applied the certain potential, the H plus and OH minus which are coming from the dissociation of water will transport toward the oppositely charged electrode, and you will find the discharge of the H plus into the hydrogen gas, and discharge on the, that is on the cathode, that is nothing but the reduction process, and the oxidation on the anode, as oxygen will be coming out. So oxygen on the other side, which is again we need, is a greener product, and hydrogen, which is a cleaner product, as the source of energy we can get it, right? So but even though it is a very simple electrolysis process as given by the means like Faraday, Faraday's first law and second law says how the electrolysis works, but the problem with that is the electrode material, because at any interface, any gas, liquid gas or the even solid liquid interface, the interface is not stable for a longer time. Sustainability is the big issue. So electrodes will not be stable for a longer time because again, especially if you are doing the electrolysis, the acid or the strong base is the electrolyte commonly used. So in connection with this, the material which is at this interface will not be stable, will get infected and will become oxide, with the performance will not be there. If the initially 100 to 100 electron transfer are there, that will reduce by once like a few months we cross it, right? So that this problem we need to resolve. And then there are elements like a platinum, like a tungsten, iridium. These elements are stable, but unfortunately the cost of these elements are more. So because of that, the commercialization will get locked. And unfortunately for the electrochemical system is the common issue. Even though if you are talking about the mobiles and the life of mobile and battery for comparing, we have the life of battery is half of the life of your electronic circuits or the mobile, you can say. So this problem is common, and we are, as a chemist, we need to work on that. One issue is to reduce the cost, to avoid the coinage metals like a platinum, to find the alternative which is affordable to the common people, and another is to make it sustainable for a longer time, right? So by this way, so these are the issues. So people are trying to shift from the platinum to the non-platinum. Platinum coupled with some other elements which supports to the platinum. So which will not allow, again will reduce the cost, plus will make, keep platinum is active for a longer time. So this way development of new material is there. So there are the issues which are associated with, if you are talking about the hydrogen, so transportation, storage is the issue, is very explosive. Another, if you are talking about the electrodes where the intermediates like hydrocarbons we are using, the oxidative products like a carbon monoxide or oxygen will come out, and carbon monoxide we know is the strongest ligand in series. So that irreversibly blocks some of the active sites that is not good for us to as far as the performance has concerned. So we have the some other, if you are making the systematic bimetallic nanoparticle, so this ruthenium will support to the platinums with respect to their carbon monoxide blockage. So, but we cannot systematically arrange platinum, ruthenium together. Sometimes if the mismatch comes, the platinum together will become the patch of like carbon monoxide blockage, right? So then development of efficient electrocatalytic system which help us to do the straightforward electron transfer, that is actual we can consider as a challenge, and we can work on that, right? So as far as the water splitting is concerned, we have the process of 2 electron transfer where the hydrogen molecule will get formed from the water, and another side where the oxygen is there. See, if you are talking about the electrochemical system, both electron transfer processes depends on each other. Somewhere if you are concentrating on the oxygen production, automatically another side where we can collect the hydrogen on the other electrons, right? So this way people are developing the material which is support for the hydrogen production or for the oxygen production or for both, right? If you are talking about how this hydrogen will get formed on the electrode surface, if we have the electrode which we have made as a cathode, electron transfer, that cathode will support to give the electron transfer, will be having the centers of the electrons on the surface of the electrode. So that centers will attract the positively charged species from solution, and that will get adsorbed. Once that adsorbed, so automatically that adsorption followed by the electron support from the electrode surface, automatically the positive charge of H plus will get down and will become the negatively charged, like a hydride type of things. So another H plus will come and will catch that hydride form of hydrogen, H plus, and suddenly that will be molecular hydrogen will discharge from the surface. You will find the micro bubbles are getting on the surface. So by this way, the hydrogen will get produced on the surface. So this pathway I have shown here. So similarly, we are talking about the oxygen to generate. So we have the peroxide mechanism is always is there for all majority of the electrocatalytic system. So OH will come adsorb, there will be the electron transfer and result into the H plus will get detached because of the another OH minus present from the solution. So by this way, this OH minus followed by another OH will come and will become a peroxide. And this detachment of the H plus, we see the 1, 2, 3, 4 electron transfer where the little complex compared to the hydrogen generation, but oxygen generation is also possible to support for the production of hydrogen. So as a part of that, I will give some examples how to develop a new material which is efficient for such type of processes, right? What we have done here, we have synthesized the graphene oxide. Graphene oxide, we can do the acid treatment to the graphite where we can oxidative removal of the surface sheet that we can do, and that further reduction of this oxidized carbon result into the formation of the pockets on the surface. So this we can say is the defective graphene, and we have treated this with THF borane. So where we are expecting this borane will systematically go and settle on this place where the vacancy is there, and we have got a boron substituted graphene. Systematically, what we are expecting the small size boron on the sheet of a graphene where there is no scope for the electrons to stay for a longer time. Whatever the electron is supported from the cathode, that as such straightforward should go to the H plus. So that responsibility has taken by this boron and is become it's like a shoring of the electrons to the H plus, and we got the conversion of this H plus to the molecular hydrogen here. So that we have confirmed, because the problem with this is that boron should not catch the oxygen and carbon oxygen borons, that linkage should not be there, because the oxygen will block the further electron transfer, because the graphene is the source of is a platform for the electrons to transfer. So that possibility which we have checked by the X-ray photoelectron spectroscopy, where the boron carbon bond which we observed in case of the boron, and where the boron carbon is there in case of the carbon. So this supports for the hydrogen production. I don't want to go in more detail, but the performance wise, this new material, that is boron substituted graphene, which is better than the systems which are existing, even the platinum. So this carbon based material is better than the even the platinum, right? So another work where what we have done, we have modified this graphene with the phosphorus, where the phosphoric acid and phosphorus acid, these two systems we have tried. The oxidation of phosphorus matters for the performance, and that we have confirmed. So compared to the defective graphene, the onset potential is changed extensively, and we got a better performance here as far as the oxygen generation is concerned. That is supported by some spectroscopic characterizations, right? So in another work, what we have done, we have tried to make the carbon nitride. Carbon nitride, this is nothing but a network of carbon nitrogen together, right? It's a very high semiconducting system. But if you heat it, fortunately what we got once we heat it at 700 degrees centigrade under the inert atmosphere, we got a nitrogen doped carbon nanotubes. And this systematically having the two different types of nitrogen which are responsible for, because see, if you have the seat of a carbon, and in that seat somewhere we have the defective side like heteroatoms, that becomes the active site, I want to say here. So such type of nitrogen based active sites we have developed, and that content is more because this is already structural nitrogen. So that nitrogens which we have used for a certain performance, and we got a better performance as far as the hydrogen generation is concerned on this, right? So another metal-free system where what we have done, we have modified this graphene with acid functionalization treated with ethynyl chloride to make it is like a living group and is modified with the amino acid like lysine. So this terminal amine group is responsible for the adsorption of OH minus and result into the oxygen generation, which we have observed here. This is the mechanistic pathway I am showing. So another material where what we have done, we have used the multi-walled carbon nanotubes modified with again amine, and this is the bifunctional electrocatalytic systems which where we got the hydrogen production also at lower potential possible, and oxygen generation also at a lower potential. So another system where the graphene we have modified with the tyramine, and this modified systems is used for the water splitting reaction. Especially why this material is good compared to the metal based modification is that the metals, if you are using on the carbon sheet, there is a possibility of leaching. So the nanoparticle will detach from the sheet and the performance will come down. We cannot expect the hybrid performance, like their synergetic effect toward the improvement in a performance will be not stable for a longer time. That is the problem that we observed actually. So here, as far as the metal nanoparticle decoration is concerned, where nanospheres of rhodium we have decorated on the graphene, and because of this, even though it's expensive, the small content of the nanoparticles will change huge as far as its performance is concerned. So here we have made the cost-effective system by decorating the nickel and nickel oxide based nanoparticle on graphene oxide, and so this performance is again better, or compared to the platinum is not crossed platinum but is reaching near to the platinum, but it's cost-wise if you are talking about nickel and platinum is huge difference in a cost, right? So this is cobalt based system. So where it is good system for the oxygen generation. This is the mechanistic pathway, how the oxygen generate, how the oxygen produce on the surface of this one. So another cost effective system, which is where the multi-component we have used, that is CZTS. C stands for copper, Z stands for zinc, T stands for tin and sulfur. This together will become a chalcogenide based systems, like a complex network, but individual atoms into that are more active, that we have showcased for the hydrogen generation. Especially this is good material for the photocatalytic also, because these together will become a semiconducting system, right? But we have tried for the electrocatalytic studies, and further we have modified this with the cobalt, nickel, iron, and performance we got is a tunable performance. Right. Further, this CZTS we have coupled with another potential candidate like graphene oxide, and we got a better response as far as the change from the graphene oxide to the this much difference is there as far as the performance is concerned, like around 800 millivolt reduction in potential that we have observed. And if you couple this with CZTS and modified with the amine functionalization, again the adsorption sites will be high, and we observed the performance wise major change here. You got means like a 2.5 to 1, means like 1.5 volt difference, this much big difference which we have observed here, right? So hydrogen production from other species means like we have there is no only we don't have the limit with the hydrogen from the water, hydrogen from the hydrocarbon. So there are other species like we have the hydrazine, where the hydrogen reach, and again the output means like a side product will be like a nitrogen, which is a greener one, right? So another like H2S. We can take out the hydrogen from the hydrogen sulfide also. So that possibilities are there to develop a certain material like MWCNTs with a composite with a graphene oxide, which is used for the hydrogen production from H2S. Here the hydrogen oxidation, where the hydrogen we got from the hydrogen, where the silver nanoparticle which we have decorated on the C60, and this electrocatalytic systems we have used for the production of hydrogen from the hydrogen, right? So another system where the hydrogen oxidation which we have seen, that is cytosine modified with the graphene oxide, cysteine modified with the graphene oxide, where we have used hydrogen oxidation process on the surface. Right. So another system where the conversion of isopropanol to acetone, which we have done on the nickel oxide modified with a nitrogen sulfur containing carbon sheet that we have synthesized by the basic component like aniline, functional aniline with treated in with a nickel oxide, and we got this composite system, and that we have used for the conversion, which taking hydrogen from the isopropanol, and that we have supported by the electrochemical and product analysis data. So this hydrogen, whatever may be the hydrogen which we have produced, how to use it? Use as a fuel in a vehicle is the one way, but we need to convert into the electricity, that is another way, where the fuel cell works. So in fuel cell, the major component is hydrogen which is there. So that hydrogen we can supply on the electrode, where the oxidation of hydrogen into H+, that H+ will go to the cathode side, and the electron which is generated to the external circuit will come to the cathode again, where the reduction of oxygen is there. So again, where the electrochemistry is involved for the oxidation of a fuel-based material, and the oxygen reduction is the another problem which is there to whatever the oxygen is there in an environment. Develop an electrocatalytic system which help us to reduce oxygen to the OH minus at possible lower potential. Right. So in that way, we have developed the electrocatalytic system. Here I am talking about the rhodium-based two different capping molecule we have, because see, if you are doing the colloidal synthesis, nanoparticle we need to control their surface by the passivation. So to passivate the surface, the organic molecule, functional organic molecules will do the major role. So what they does, the functionality they will engage with the surface adsorption, and will make the pack the surface, and will not allow the another atoms to go inside, or the atoms from the particles to go out. So this we can make the protection from the surface. So for that we have used two different molecules like a tartaric acid and ascorbic acid, and we got a chain type of assembly because of the polyfunctional nature of these molecules, and that chains we have used for the electrocatalytic fuel cell reaction, where the formic acid conversion we have observed, and tunable onset potential and current density we observed. Here rhodium hexamethylene tetraamine based nanorods we have synthesized, and having the better performance that we observed. So in another case, what we have done, we have used the aluminum foil for the reduction of rhodium ions, and that reduce rhodium ions systematically on the sheet of or on the surface of the carbon nanotubes. That we have done by this pathway, and that is carbon nanotube we have acid treated, we have generated the acid functionalities, where then treated with the rhodium chloride, rhodium ions will replace this H+ and will be settled like a Lowry Brown state concept, and we got the adsorbed rhodium ions here, and we just dipped the aluminum strip into that solution. We got the decoration of the nanoparticle, because this will support for the galvanic type of replacement of electron transfer to the rhodium ions to get the atoms, and that atoms collectively become a cluster, and that cluster will be there on the place where the sites are available on the carbon nanotubes. We observed such type of nanoparticles, decorated carbon nanotubes, and this we have used for again for the fuel cell reactions. In another work, what we have done, we have used the high temperature route like a CVD route for the development of the different nanoparticle. The structural transformation from the rhodium acetate is having like the complex structure, so that assembly will get convert at 500 to the like a cubical structure, then we'll get the like a tetrahedral structure, then to the hexagonal structure. So this transformation will make the structural changes also. So we have observed in case of the cubes, we have the asymmetric growth, because atoms, those who are having the symmetry, so that atoms are not active atoms, I can say. So what we need to do, we need to develop the atoms which are asymmetric. There should not have the at least one or two neighbors far away, or there's not there on that side. So that atoms are more active. So such type of atoms will be responsible for the interaction with the formic acid type of molecules, and we got, and that we have confirmed. So the ratio of highly symmetric to the low symmetric planes, if you compare the intensity wise, we have seen the cubes are more active. Such type of correlation we have done here. Another case where the bifunctional molecules like nanospheres we have synthesized by the naphthalene and camphor as the source of carbon, and this material we have used for a different purposes, especially here for the direct ascorbic acid fuel cell. As a fuel, ascorbic acid we have used, and that conversion we have tested by the electrochemical studies. So another bimetallic system like bismuth cobalt system developed for the ethanol oxidation. So same by the solution route, graphene oxide we have made, decorated with the bismuth, and further we have just treated with the cobalt ion, where we got a systematic decoration of the cobalt on the head of bismuth, and that bismuth cobalt bimetallic system is there on the graphene sheet. So because of the cobalt, bismuth becomes active. As such, bismuth is not active for this conversion. So that we have tested here. So another work where we have done the nickel decoration on the graphene, and that we have used for the urea oxidation. Similarly, here we have talked about the hydrogen oxidation, that is the hydrogen production, that is direct hydrogen fuel cell we can use. So these are the some examples where the different systems we have synthesized for the urea oxidation reactions. So here bimetallic system like iron nickel alloy nanoparticles we have used for the urea oxidation. This is recent work I am showing here. So here graphite powder we have used the functionalization to the graphene oxide, treated with the sodium borohydride and modified with the surface with the bismuth. So bismuth cobalt system we used for the formaldehyde and urea oxidation reactions. So meanwhile, again, along with this hydrogen production, hydrogen utilization, we have worked for the electrochemical waste management also, where the different reactions for the environmental protection we have done here, especially here. So nitro means NO2 gas sensor followed by the conversion that we have done by the electrochemical system, that is NO2 minus to the NO3, means like a harmful to the harmless. That conversion also we have done. Some like a drug or some like a waste, means like organic waste management, that also like a semi-carbazide conversion, that also we have studied. Same examples I'm not showing here, just more. So another, in line with the earlier talk, we have worked on the carbon dioxide reduction also. So we got a project from the DST for this electrocatalytic carbon development of a new material for the carbon dioxide reduction. The problem with the carbon dioxide is that it's tunable products with the potential, and unfortunately we have the limit. If you are working in a aqueous system, unfortunately window is very small, like a 2 volt, like +1 to -1 via 0 is become a 2 volt, and 2 volt is not enough for the carbon dioxide to reduce. We need to go beyond. So then people have shifting from the aqueous system to the ionic liquid based system, where this coordinating solvent will support, will interact. Another beauty of this ionic liquid based system is that will accommodate the carbon dioxide effectively. In aqueous system, solubility is not much or is not there. So we need to modify the aqueous system. But in ionic liquid, the solubility is more the carbon dioxide is possibility to get a more product is there, and the actuation barrier will come down. So this was the objective, and there are few examples where the manganese oxide graphene means like a carbon nitride based system, zinc oxide based system, alumina based system, bismuth based system has tested for the carbon dioxide reduction work. So with this, I can say the impact of metal-free based systems are good for the energy conversion. Also the hydrogen, we can say the hydrogen production, or even for the conversion of hydrogen to the electricity via fuel cell. So where the new materials supports dominantly, we can say. The reason behind this is if you go toward if you are modifying the system, the new properties from that material we can expect, or we can utilize for certain applications. And this modification is possible these days because of the development in microscopic techniques. We are able to see, then if you are able to see, you are able to modify it. Right? So these possibilities are there in our hand. So with this, these are my academic collaborators in international and national. Of course, this is not possible without the active hands and brains. So the majority of work corresponding to the hydrogen production I am showing here, which has done by the Renuka, Vijay, some part by Ajay, major by the Shankar. Now Somnath is working on the same line. The CO2 reduction where the Balaji and Ajay has contributed. For the hydrogen production from other systems, Pratiksha, Rohini is working on that. Ravi, Parag, Shiva, they have worked on the environment management based electrochemical reactions. With this, thank you. Thank you very much for.
Hello. Yes, nice. Thank you, Professor Bhaskar Sate, sir. Any question from the audience? From student sides. Try to generate the question, try to design the question. Yes, sir.
Binding capacity of reduces in due course of time. Will you elaborate this little bit?
And size of?
Cement.
Binding size of the cement reduces in due course of time after few months or why?
Actually, if you talking about the size, if you go toward the lower size, the surface atoms are more. This is one case. It's not only more, their dangling bonds are more. Because of what we are doing, we are making a small miss what? We are cutting it. Somewhere we are breaking the interaction with each other. So if you are individual particle, if you are talking about the large number of atoms are there on the surface, they are ready to, they are in a search to find some other member where they are to hold them. So in that way, if lower the size, holding capacity is more. But what happens, one particle comes together, another particle join, automatically their capacity, holding capacity comes down. The reason why, the number of atoms become satisfied. They will not be in a search with the another particles where to hold it. Right? So in that case, if they're comparing initially, if the particle was, today the particle was in a 5 nanometer, just imagine. But unfortunately, they got another neighbors, and tomorrow or day after tomorrow, they becomes 10 or 15 nanometer. Right? So the next day's particle is more satisfied particle than today's. So automatically their holding capacity comes down once we go toward the, or once we pass with some time. So this is the problem with the cement. That's the reason why after 1 or 2 months, the cement of no use. We need a fresh cement always.
Okay, thank you.
Another question, production of hydrogen and its utility. Nowadays, the cars are run by the hydrogen, what I have read. So, will you explain it?
Yeah. If you are globally, if you are talking about, there are small countries where their problems are different. They are well satisfied with, means like they are rich countries, we can say. They have to extend their life, because see, because of this pollution nowadays the life is, general life is in percentage wise reduced by like a 20%. Means like earlier 80, 85, 90, nowadays 50, 55, 60 is the common life, we can say. So this big problem is because of the pollution, right? So then zero carbon policies they have implemented, where we are targeting at 2050. As a India, we are targeting as a zero emission of a carbon is in a 2050. So that people are implemented already, but their rules, regulations are very strong. They are only concentrating on the zero emission of carbon in environment, where they are using hydrogen as a fuel in a vehicle. So the population is not much. Vehicles on roads are very less. The possibility of accident is actual zero. Everybody is following the rules and regulations of a road. Roads are quality. Here for the hydrogen is the problem. If you are using a hydrogen as a fuel, if you fill the tank by the hydrogen, we can use that for 5-6 months continuously as a energy. But unfortunately, small shock is more enough to blast it. So to avoid this issue, either we have to be very straightforward, very serious about the rules, road rules. Accidents should not be there. Roads should be with a high quality, right? So this possibility, this making delay here in India. Actually, in front of us, there are different issues. So we are not shifting toward the hydrogen, because we are, even though for the fossil fuels, we have the dependency on other countries, right? So these are the issues in front of us. But yes, there are some countries where the hydrogen-based fuel cell or hydrogen fuel-based vehicles are there. Yes.
Yes, anyone? Yes.
Hello. What does it mean, white hydrogen, blue hydrogen, and green hydrogen, and among them, which is cost effective?
As far as hydrogen is concerned, the source, which source we are using to produce the hydrogen, that decides this quality, right? Especially if you are doing the electrochemical production of hydrogen from the source like either hydrogen, ammonia, or water, where we'll get a green hydrogen. There is a completely free from other impurities, because it's a gaseous species which is coming out. So there is the possibility of other impurities also. The cost wise, yes, it's very difficult to get the green hydrogen, but yes, is a challenge actually.
First of all, it was a very enthusiastic lecture. Then I want to ask sir that the starting material for the production of hydrogen was some graphitic carbon nitride. Okay, so I find some literature about band gap energy having minus 2.7 electron volt. As you proceed further, so you have make some porous material by unwinding some position on that, so making space in that. So I want to ask if this procedure have any impact on band gap for and having for the semiconductor property.
Yes, actually, the people are working on the doping of some other metals, non-metals. So in that case, if really that metal is incorporating structurally in a material, then only we can say the band structure is getting changed. Otherwise, in most of the cases, that comes from the synergetic effect. Somewhere we have the cluster, and that is on this platform. So this platform is supporting these two, and then the individual identity or individual performance will get changed, and the collective performance will come out. That collective performance, of course, both are the active candidates. So because of them, the overall performance will become a better. So by that way, you will find the better performance as far as the application is concerned. But individual, their structural identity you will observe, especially if you are talking about the X-ray diffraction. You will have the two phases, independent phases. But if the structural doping is there, yes, either we'll get the shift in a band, their position of a plane will get shift, or if you are going for the energy calculation, you will find the band structure is getting changed, right? That is there.
There is no questions from the audience. I would like to thanks Dr. Bhaskar Sate sir for giving very excellent talk on new modification in material for hydrogen generations. He have explained why to develop the new materials very nicely, surface charges, then why gold show the different color. How we fabricate the nanomaterial, nanostructure, carbon allotropes, have different allotropes, you have explained very nicely. Then changes for what will happen, what are the challenges next 50 years. Clean year is the very important challenges for next 50 years. Then hydrogen, why water as a starting materials for generation of hydrogen. Then water splitting, nano electrode for water splittings. Then he have used the different metal ion which is supported on graphene, that is boron supported, phosphorus supported. Then modification of carbon nanotubes, CZTS, nickel supported polyanilines. It is a very nice talks, excellent talks, and I am very happy to congratulate Dr. Bhaskar Sate sir, giving very excellent talk. Give big hand to him. Thank you very much.
Thank you, sir, for insightful presentation. We are truly grateful for sharing your valuable insights. You have explained from fundamental basic concepts of nanomaterials towards the application, how hydrogen is generated and utilized for as an energy source. So thank you, sir, and thank you, Lande, sir, for chairing the session. So today we have very eminent our faculty. So I want to, sir, I am asking to all of you, can you give remarks on this series? नहीं है, नहीं है, नहीं है. So we have honored to have with us distinguished guest Professor Manik Ravji Solanke sir. So I humbly request Professor Manikrauji Solanke sir to conclude the series by his invaluable remarks. Manikrauji Solanke sir.
Hello.
Yes, sir, you are audible.
Okay. On this particular day, I pay respect to Professor Ingle, who is responsible to develop chemistry department in Dr. Babasaheb Ambedkar Marathwada University, along with his colleagues, and I could see the colleagues are present in this particular audience. Dr. Ashwin Deshpande is there, then Dr. Singare, Dr. Mani, and so many others, even from biochemistry, Dr. Somans is there, and I'm really happy. Today, both the lectures were on the theme, which is very important as far as the sustainable growth of our country is concerned. In SDGs, Sustainable Development Goals, it's very important to have the green energy. And particularly, we are facing a lot of problems. See, everybody talks about CO2 emission, but the real problem is when we try to control CO2, particularly for developed countries, the problem is very serious because the the industrial growth will be reduced. And that's why in G20 meeting also, we are not in position to say that we would like to reduce the CO2 emission because of all these things. And I really appreciate both the speakers that they could explain how our country, even Dr. Pulsik Tiwar was trying to explain how the things will be commercialized. And I hope also Dr. Bhaskar will develop some technology by which the things will be commercialized. Very difficult thing. And already Bhaskar has mentioned about how difficult to use hydrogen as a fuel, what are the problems are associated. Considering all these facts, I think we should do more research. We have to spend more efforts in commercializing the technology. Particularly in our country, the commercialization is becoming a great challenge. I would like to thank organizers for organizing excellent. Both the speakers has delivered very nice lectures, and I appreciate organizers for their work. I thank one and all for their efforts. Salute to contribution of Professor Ingle. Thank you, all. Namaskar.
Thank you, sir. Thank you, sir, for your valuable remarks. Sir has been a great chemist and he has held a vice chancellor position of 5 universities. So thank you, Manikrauji Solanke, sir. So as we inch towards the closing of this event, I invite Professor Rajita Ingle, a daughter of late Professor Ingle sir, to pay vote of thanks.
Say good afternoon, everyone. So on behalf of convener and organizer, I pay my gratitude to the distinguished speakers of this series, Professor Vivek Polshettiwar and Professor Bhaskar Sate sir, for their enlightening and motivating talk. I am thankful to the chairperson, Professor Satish Patil, and Professor M.K. Lande sir for their inputs and sparing their valuable time for this series. I express my gratitude, sincere thanks to all the to head of the chemistry, Professor Shankarvar sir, Professor Mane sir, Professor Shingare sir, and all faculty members of the department, Professor Gaikwad sir, Professor Anjali Rajbhoj madam, Professor Shingte sir, Professor Lande sir, and Professor Sate sir for their cooperation, participation, and organizing Professor D.B.Ingle sir, 5th memorable lecture series. I also thanks Professor Deshpande sir, Professor Rajbhoj sir, Professor Arbat sir, Professor Shomanshi sir, Professor D.R. Mane sir for their presence. I also thanks Professor Manikrao Solunke sir and Professor R.P. sir, R.P. Pawar sir for their participation. I thanks university authorities for providing all the facilities for required for the smooth conduct of this event. So lastly, I am thankful to all the students, participants, researchers and teachers who had participated in online and offline mode. Thank you.
Now the series is over. Thank you all of you for joining with us online and offline mode.